And we're live with the next talk. Today now we're gonna see about the talk from Nikolaj Fogh, who's gonna talk about variable monitoring with declarative interfaces. Really interesting topic, which I think applies to a lot of our work. So please take it away, Nikolaj.
Thank you. I'm Nikolaj Fogh, and I work at Siemens Gamesa. And I'd like to show to you some approaches and some methods for large scale monitoring in like industrial control systems. I'm not going to show you a recipe that you can just use right off the bat for your things, but it's more going to be if you can pick up some ideas and some techniques that you might be able to employ in your software project. So that's kind of my hope for this talk. So a bit about me. I have a background in electronics engineering and in process control. I started doing mostly embedded C work. For the last 10 years, I've been working mostly with C++, so a bit higher level. I've been in offshore oil, gas, and renewables. I've been in the defense industry and in automotive. And I've had something in the medical industry. And last but not least, here now in the energy and again in renewables. So that's short about me. So first I'd like to talk a bit about like Siemens Gamesa. I always find it interesting in these talks to know about a company and how they use C++ to solve their problems. And I guess it comes as no surprise that we do wind turbines, so we do big offshore wind turbines and like some slightly smaller onshore wind turbines. I'd like to talk a bit about like what goes on inside of these things. Like usually, I guess you just drive through them or drive past them maybe every day. So what is going on in one of these? But first, a bit about the people that work here. So we have a very large range of backgrounds. Like we have people that are good at math, we have physicists, we have process control, which I'm part of as well. We have people that are very good at mechanics and hardware, and also we have people that are good at software. But the thing is, it's not everybody is equally interested in the software part itself. Like they use software as a tool to solve their problem, and that's basically what software is. It's just a tool that we use to solve a problem. It's a very good tool, and it's a very flexible one, but it's still just a tool. Some people they prefer just having a one-liner to instantiate some fairly complex logic. They don't want to understand like if there's some intricate software design behind all of this. They just want to get their task done. Now we can't all get tears in our eyes when we see a beautifully written piece of software. This is software engineering, so there is some compromise between pragmatism and delivering something and idealism. So we do need to deliver projects, and one of my jobs is to give people the tools, some suitable tools that they can use to solve their task. So back to the wind turbines. So what goes on in the software for a wind turbine? So I'm going to give you a quick brush up. So in a typical 7 megawatt turbine, you actually have a complete generator, a whole power plant up in the nacelle here. And we have around 450 different kinds of sensors that monitors everything that goes on. We have around 150 different actuators. We have valves, we have pumps, we have fans, we have motors. We've got basically everything. Here we even have a sensor, which is basically a microphone that can sense if some technician has lost a tool while he was up there and it starts to make a lot of noise. We have a sensor for that. So a lot of sensors. Our code size with around 2.5 million lines of code, so fairly sizable piece of software. And what this software does is like primarily we want to optimize power production. So that can be something as simple as like turning the wind turbine into the wind if the wind direction changes. Of course, we need to pitch the blades in the right way so we get the most power out of the wind. One other thing we do is that that we have some control software where we try to minimize mechanical loads on the turbine, because if we can do with a thinner tower, we can save on materials, and that makes it cheaper to produce the turbine, to install the turbine, and all that. And that you can actually do in software. So that's another thing that we do. Last but not least, we need to monitor a lot of state, and we need to report alarms if there's something not working quite well, and we need to take action in case there's some kind of undesired behavior. Like, for example, if there's overcurrent in something, maybe we need to throttle power output a bit. If there's smoke in somewhere, probably good idea to shut down the turbine or something like this. That can be different kind of criticalities in this, and we do need to deal with each of these in different ways. And we do this by controlling all these valves and pumps and fans and motors. So that's brief overview of what actually goes on in a working wind turbine. And what we use to control all this, that we have some PC, some industrial PC, not unlike the one you see here in this picture. It's running some publish subscribe middleware, which allows us to have different components talking together. Some of the components might give us some hardware access to all these sensors, like to read in data and to send out data. We've got a lot of state machines running, which controls all the different subsystems that you have in the turbine, all the states in those. For this power optimization and mechanical loads, we have a lot of algorithms that where we have models of the wind turbine, where we can see, okay, if the wind is like this, how should we pitch the blades in order to get the maximum amount of power from this wind turbine. So we have a lot of algorithms that are running on this one for control as well. And last but not least, we have the monitoring, which will be the focus of this talk. So yeah, we can look at monitoring a bit in detail. So basically it means we have some signal that comes in. It can be some kind of measurement. It can be some derived value, like two measurement that you merge somehow, and that's another signal. Or it can be some manual input. You could have a technician in the turbine with his tablet inputting some data, or setting valves manually or something like this. And those we need to do some kind of check on. So is it in range? Is the status good? It could be any kind of check. And once we've done the check, we need to do some kind of response. So the response could be control an actuator. For example, put the wind turbine into the wind if the wind changes direction. If we have some kind of unexpected situation, maybe we want to set an alarm. We can also stop the turbine. We would try to do that as the last resort, because it is very expensive to stop a turbine. So if we could rectify it somehow, then we prefer to do that. So that's basics that goes into monitoring. And that allows us to give us our problem statement. Now, how do we give our developers, how do we give them some good tools to create monitors? But the problem is here, how do we measure good? Of course, it needs to give us the functionality that I just mentioned, but there's more to it than just that. There's these things called quality attributes, like the non-functional requirements. I've taken some from this book. It might be a bit high level here because it deals more with software architecture, but it has a list of some non-functional requirements. I'm going to mention some of the ones that are quite important, especially for this and for this kind of software. The first one is scalability. As I said, we have a lot of inputs, we have a lot of outputs. We have even more monitors that monitor all these things. So we have several hundreds of monitors. So you need to be able to scale your monitors quite well. Another quality attribute is usability. Bendine, he had a presentation, I think, that was called "Make it easy to use and hard to misuse." And I think that should be the first mantra for any library and utility developers, because it is so important that it's easy to use this. If it's hard to use, then the users will just not bother, or they'll not be happy with it. And it's I consider this to be one of the most important things. Especially, I consider readability to be part of usability as well. So yeah, a very important attribute. And the last thing I'm going to show here, that is modifiability, because as we all know, change happens. We have a new requirement coming in. We need to be able to modify our software. I don't think any software has ever been written that has not had to modify in some way. If you write your software not to be modifiable, you're doomed to failure. So we do need to have something that's very modifiable. Yeah. So with those in place, let's get started. I'm going to show you 3 different approaches to this problem with monitoring. And then I'm going to give them scores for these quality attributes. Now, they can all solve all these functional requirements, but I'm going to look at how they solve the non-functional requirements as well. And the first one I'm going to look at is the ad hoc approach, which is the one you usually just start out with when you do some solution. Now, much of this code is slideware. Like, it has been working at some point, but then I copied it into the PowerPoint and had to change a bit here and there. I've done way too much coding in PowerPoint for this presentation. And I'll tell you, PowerPoint is not a good code editor. So if you take anything away from this presentation, it should be that. Anyway, here goes. So this is some code that could be an example of some kind of publish subscribe framework that gives us the ability to subscribe to signals and to send signals, and in this case also alarms. So the subscribe here is a function that subscribes to some signal, in this case mSignal, and we can set the handler which handles whenever this signal changes. And here you can kind of read what's going on. So whenever mSignal changes, if the value is in the range from 0 to 1, then we disable this alarm. Otherwise, we set the alarm. And that's fairly okay. It's quite easy to reason about. The problem with this is that it gets complicated fairly quickly. Now, let's imagine we have some signal that's a bit noisy, so we don't want to immediately set an alarm the first time the value goes above 1. So instead, we want to have a delayed alarm. So instead of setting an alarm immediately, then we start a timer. Let's say we wait 10 seconds. If it's still not in range, well, then we want to set the alarm. And if it's in range again, we need to stop the timer and we need to disable the alarm again. And then it gets complicated fairly quickly. Now, it's not immediately easy to read what exactly is going on here. What is the core logic behind what's going on here? Now, this is still a fairly simple example, but it can get quite complicated very easily. One more thing is that it's very easy to make mistakes, especially when you start scaling up a bit. If you need to do 100 of these, what is the risk of you forgetting to stop the timer in the else clause? It is fairly easy. I should get caught by testing, of course, but we know that doesn't always stop bugs from coming through. So this is one way. This is an ad hoc approach. You can do that fairly quickly, but let's look a bit at the quality attributes here. So I'm going to start the place where it's really good. So modifiability, it gets top marks, because you can modify this code to your heart's content and you won't break anybody else's code. Is really great for modifiability. Oh, I would say usability is not the best. In particular here, I would say readability is not that. You can get all the logic from reading the code. That's a good thing, but you do need to read quite a lot of code in order to understand all of it. So usability is not really optimal. And you do need to write a lot of code as well if you want to do a new monitor. There's a lot of like explicit logic you need to do. You probably need to do the same thing over and over again. So usability is not the best. Scalability, again, it also comes to the fact you need to write the code again and again and again. If you have this code out 100 different places and there's a bug in some of it, you need to modify it 100 times. So for that, it doesn't work that well. But I think quite obvious, the ad hoc approach only works for very small problems where it's quite specific. It doesn't scale at all. So let's try a second attempt where we use classes to get some code reuse from this. So we could make some classes that contain all of this business logic that we saw before in this ad hoc method. So here we have two different classes, one called, well, we have a component first, which has these three monitors, two different types. So we have a monitor signal quality and we have a monitor limits. And in our constructor of this component, then we can construct these monitors. Now notice here, we got this little O parameter as the first one. And the O parameter is just some kind of handle to this publish subscribe framework. It's not really important for the sake of this presentation exactly what is in that, but just know that is a way to subscribe and to send signals with this. I'm going to use it a bit through this presentation. But the good thing here, you can kind of read what's going on here. Like we have a monitor, we monitor water pressure A. When the signal is bad, we want an instant alarm of pressure alarm. For the wind speed monitor, we want to monitor wind speed. When it's higher than 10, then we want to send out the signal wind speed is high. And it's quite nice. If the classes are coded fairly sanely, you can reason about what's getting done without having to go through all the if then else clauses. It's it kind of reads out like you would read a text. Also, because we use this pops up framework, I would argue it's a declarative interface, because once we have instantiated this monitor, everything just kind of works. You don't need to worry about it anymore. And that's a very good quality to have for some developers that don't want to explicitly call the monitor every time and do all these checks. They just want to instantiate it. They want to read what is it that's getting done, and then think the monitor just needs to do its thing. So it's very good for our developers here. Yeah. So as I said, it's a declarative interface. Now, there is one problem with this approach, which is the passage of time. So, as you probably also tried yourself, people want some new functionality, no problem. We just add it to this monitoring class. It doesn't quite fit the bill. It's not covered by this monitoring class. You make a new monitoring class, you do a copy and you change it a bit, and then I think you see where this is going. All of a sudden, we have 18 different monitoring classes. Some of them are completely different. Some of them inherits a bit. It's a bit of a mess. And we've actually worked a bit with something like this. It works for when you don't have too many monitors, but when it gets more specialized, you get a lot, and it becomes a bit of a pain to work with. And I think that the reason this happens is because it broke some of the solid principles, in particular the open-close principle. Like every time we need to add some new functionality, you open up the class, you edit a bit, and then you get on with your life. But you risk here breaking somebody else's code, and that's not really good. You can't do your changes without everybody having to recompile everything, and it's not really good. So we can look a bit at the quality attributes for this solution. And here we do have scalability. It's very easy to make a new class. You can make hundreds of them. You can even put them all in a container, and it works. So that's quite nice. Usability is also good. As I said, you can readability in particular. You can just read what's going on. And again, it's easy to make a new monitor. It's for that, it works quite well. However, modifiability is really not the best. It's hard to modify these. You need to go in and open up the code, find out what was this guy thinking for this particular monitor, and that can be quite hard. You also need to find which monitor can I use for my particular thing. So modifiability, it doesn't really get good marks. There, the ad hoc got better. So ideally, we would like to have all of these. We'd like to have scalability, we'd like to have usability, and we would like to be able to modify these. So how can we do this? Let's try a different approach. And in this one, we would try to adhere to the solid principles, which is single responsibility principle, open-closed, least cost substitution, interface segregation, and dependency inversion. I'm not going to talk about all of these, and I'm not going to focus on all of these. The ones that I find important in this one is the first two ones. So single responsibility, a class should only do one thing, and the open closed, it should be open for modification, but how it's open for extension but closed for modification. So you should not be able to open up your classes. You should not have to in order to extend their functionality. So if we try to go along with these ones and tries to design something new. So let's try to break it down a bit. So as I talked about before, we have some signal. We need to do some kind of check on this signal, and in the end, we need to give a response. So in this diagram here, we have some signals coming in. We need to check some kind of condition. If that condition is violated, we need to call some amount of handlers. And we want to be able to customize all of these things. Now, in reality, this condition will probably be a compound of many different conditions. So we have condition 1 or condition 2 and not condition X or something like this. And that we would like to be able to do as well. So imagine now the following monitor graph. So we have my signal that comes in. It could be the wind speed. It needs to be larger than 2 and smaller than 10. And if it's not, we need to print a violation. That we would like to have something like this. So we can try to express that in code. Like note here, I'm going to approach this not from the implementation side, but from the API side. So how is our users, how are they going to use this API? So here we can express this in code. So we have a monitor. We want to monitor my signal with this pops up framework. Here's the O comes again. So I want to monitor my signal with the condition that it should be larger than 2 and smaller than 10. And the handler should print a violation if there is one. And that would be nice to have. And then let's say somewhere else in our system, we publish my signal with the value of 1. Then the monitor should print out violated true. If we publish my signal with 2, it should print out violated false, and so forth. So that is what we want. Now you can get quite creative with the naming here as well. Like for example, we could make it even more readable by saying, I want to monitor my signal. It must be larger than 2 and smaller than 10. When not, we want to print the violation. So this is even more readable. But you need to be a little bit careful with naming here, because naming convey meaning. So in this case, we've changed the meaning of it, because when not, it's only executed when it's not, like when there is a violation. So we would not call print violation when there's no violation. So we've changed the handler here. We would not print the false in this case. So sometimes you need to be a bit careful with this naming to make a nice API. And what's that one? That's not surprising. So I would go for the other one, where you have the generic condition and handler. Then it covers all the cases. So how can we do this? If we want an API like this, how can we do it? I propose something like this. There's a bit of template here, but it should be still fairly understandable. I propose that we do a kind of monitor builder, which is basically a tuple builder in some case. It holds a tuple of conditions, and it holds another tuple of handlers. And then it has 3 methods. And the first one, condition, returns a new monitor builder class that has added the condition that it takes as a parameter. The same way with the handler, it returns a new monitor builder that has added a new handler to its tuple of handlers. So we can kind of use these to build up the conditions, and we can build up the handlers. And last but not least, we have the operator paren, which checks a set of types, TS, for the conditions and calls the handlers. And that's it. We can use this now. I've got the monitor builder here again. I've removed all of the templated to get some space on my slides, but it's the same thing as before. So we can now use a function that creates a default monitor builder. So it takes some amount of types and it returns a monitor builder with 2 empty tuples. So there's no conditions, there's no handlers, and it just takes some types. The parameters are just 2 empty tuples. And now we can build our monitor like this, as we want it. Monitor my signal with the condition should be larger than 2, with the condition it should be smaller than 10, and each of these condition calls just adds to the tuple. So in this case, we'll have a tuple of a larger than 2 type and a smaller than 10 type, and we will have one handler in the handler tuple, which will be the print violation type. And we can change this again. Like we're flexible, because we can have a condition that says it needs to be larger than 2 and smaller than 10, and my odd condition, it can be any kind of condition, really. You can add these without influencing anybody else's code. We can add more handlers. In this case, we want an immediate alarm activation if the condition is violated, but we want to have a delayed alarm deactivation if the condition becomes non-violated again. And this we can also just add in our particular monitor. We don't need to open up a new class in order to add this functionality. We can do it in our own code only. And that's a very, very good thing about the open close principle. If you follow this, you can do these things. Now note here, I have not done the logic to deal with subscribing and calling the monitor. Like in reality, we would again need the monitor to take this O parameter, which gives us a handle so that we can subscribe to my signal, for example, and we can send out alarms if we want to. So our monitor builder would probably look more like this. We would have a constructor which pops up some kind of type that gives us a handle to the pops up framework. But given that every pops up framework is different, I'm not going to go into details as to how you can actually do this, because I can't really say anything general about it. So yeah, just note that here sometimes I skip over that part of it, but all the methods, all the tricks and tips can still be applied, even though that one is not implemented. But yes, how do you then write new conditions? So a condition is just a callable, which returns true if the condition is violated. So in this case, we can have one that says larger, it takes 2 parameters, and it returns whether A is smaller or equal to B. So if it is, then it's true, and then it's a violation of this condition. You can also take parameters into your conditions. So we can have a minimum condition, and we'll give it a parameter that it needs to be minimum this value. Here we return a lambda, which take the val is the value we want to check, and the minimum is the minimum value it needs to be. And then we just return whether this is violated. You can also use a generic lambda, makes the code even simpler. So in this case, we have an even condition, so the value needs to be even. And here we just return a generic lambda. It can be any kind of value as long as it's even. It's not violated. If it gets uneven, then or if it gets odd, then it's violated. And you can do these generic lambdas. It makes the code much easier also for all the other ones, all the other conditions that you want to make. And the thing is here that you can go quite crazy with these conditions without bothering anybody else. So here I made max variance windows. It takes a window of X samples and it calculates the variance and makes sure that it doesn't go above something. And that I can put into my specific little component which monitors this particular little condition. I don't necessarily need to add this function to some framework. It can just be local to my code, and nobody else will ever know about it because they don't have to. It's only me that's interested in this very particular condition. And you can just add it to your monitor as you would do with any other kind of monitor. Now, one thing I haven't talked about yet is that we need to do something to do this Boolean logic on conditions, as I showed here. Because given that they're just callables, you can't just do this immediately. Like you can't and or not callables together. That needs to be done in some other way. So yeah, as I say, a condition is a callable. It takes some parameters and it returns a Boolean. So if we have a collection of callables, they all return Boolean, and they take exactly the same parameters, then I would say it actually makes sense to use this kind of Boolean logic on them. So let's try to overload the operator and or. Everybody warns against it. Again, I think it was Bendine that had a talk about operator overloading, where he said overloading or and don't do it. But what does he know? We're just gonna try it anyway. So the way we do it is that we wrap our callable in a class, which basically just wraps the callable completely. Now, wrapping a callable completely is a bit tricky, but for our intents and purposes, this is okay. I should do forward and all these things, but this is slideware again. But for our case, this is okay. All you need to know is that this logical f, as I've chosen to call it, just takes a function and has an operator paren that just forwards it to the wrapped function. And what we need to do now is then add this and operator to this logical f. We also need to add the or and the not operator. And what it does is that it takes the current function that we've wrapped, and it takes another function. And then it captures those in a lambda, calls the two functions, and returns the ANDed value of the two results. And we will wrap that lambda again in a new logical f, so that we can keep on doing this and or and not, however we would like to do it. And that, of course, we need to do for or and not again, but it is somewhat the same way to do it. One more thing we need to do is that our conditions will need to get wrapped in this logical f. So before we just returned a lambda, now we return a logical f of this lambda. So not a huge change to be able to do this. So the next thing in the monitors is how can we write new handlers? And the handlers, they're even simpler, because a handler is just a function or any kind of callable that takes a Boolean parameter, whether or not the conditions that were checked have been violated. It doesn't return anything. So in this case, we check, is it violated or not? If it's not, then the monitor passed. Otherwise, the monitor didn't pass. You can also add some kind of state to this handler. So if you want an immediate alarm activation, we can have some kind of alarm interface, which allows us to set a certain alarm. We just return a lambda, which captures this alarm by reference. And we just say, if it's violated, activate the alarm. It's as simple as that. We could also add that if it's not violated anymore, then we need to deactivate the alarm. So each of these things, each of these handlers, each of these conditions are very, very simple in their own. It's a single responsibility principle a bit. They only do one thing and they do it well. So you can test them easily as well. You can test them in isolation, which is quite easy with this. You don't need to spin up this entire monitoring framework in order to check whether your individual conditions or handlers do what they're supposed to do. And I think most of these conditions and handlers, like they pass what I think we can all agree is the most important software criteria, which is the PowerPoint test. If they fit in a slide, they're understandable and you can reason about them. So you heard it here first. PowerPoint, it's good for software development. Not so much for code editing though. Anyway, let's get back to our component. So here we will try to recreate the members of our component as we had them before. So we create a monitor for water pressure A. We take this pops up framework into it. We have the condition that the state should be good, and the handler should make an immediate alarm activation of pressure alarm when the condition is violated. Same for the wind speed. We have the condition it should be less than 10, and the handler should set the signal wind speed high. And you can see it's quite similar to the previous approach that we had. It's a bit more terse, true, but you can still kind of read what it is that's going on. It's a single line that instantiates this entire handler. So I think we still have quite good readability in this. One thing you need to note is that given that this monitor here is a separate type, the component member, like the MWPM, for example, needs to be some kind of type erased type. And in this case, std_any would actually work quite well, because we're using the pub/sub framework. We only need an instance of this monitor to be able to do all the things. We actually don't care. We don't need to control the monitor after this. Maybe we need to destroy it if we don't want this monitor to be there anymore, but we don't really need to control it anymore. So we could just put it in a std_any and we're good to go. You could also do your own type of type erasure if you wanted to, if you do need some kind of handles to control the monitor. But given that it's a declarative interface, we actually don't really need to have any control over it afterwards. We just put it in std_any. We just need an instance. We don't care what type it is. It just does its thing. So we can now look at the quality attributes for this solution here. And I would say for this builder way and this thing that has the solid principles, like we have good scalability. We can create a lot of these monitors, and it's not a lot of code that we need to add. It's easy to maintain all the different things. So scalability is good. Usability, again, it's quite similar to the utility classes. Like readability is quite good. You can easily extend them if you want to. And what we've gained here is modifiability, because now we can add different conditions. We can add different handlers without having to open up this monitor class itself. And we don't need to influence anybody else's code if we want to do something that seems a bit mental to them. So yeah, I'll show you the implementation now. So what we've had now is actually mainly just which API we would like to have. But the implementation of the actual monitor builder I'll do here in about 3 slides. So the constructor of this monitor builder just takes some conditions, it takes some handlers, and it saves them. Conditions and handlers, that's these tuples of conditions and handlers. So this is all it does. There's not more to it. What gets a bit more interesting is these builder methods. But it doesn't get a whole lot more interesting because it's still just a couple of lines. All the condition method does is that it takes the condition parameter and concatenates it to the tuple of existing conditions, and then it returns a monitor builder with the new conditions, the existing handlers, and the types we want to check. Similar to the handler, it just takes a new handler type, it concatenates it to the existing tuple, and creates a new monitor builder. So that way we build these conditions and we build these handlers using these methods. In the end, we have this checker method, the one that actually does the logic in this class. Again, it is 6 lines. Of course, there are some utility functions that I have made here. I don't want to show them in this slide. I'm going to tell you what they do. So apply functions here. It just calls all the callables in a tuple with the given parameters, and then it returns a tuple of results. So in essence, what it does is this. So result 0 is m conditions 0 called with the arguments. Result 1 is m conditions 1 called with the arguments, and so forth. So now we have a tuple of whether or not these individual conditions have been violated. Any true just returns true if any element in a tuple evaluates to true. And in the end, call functions just calls all callables in a tuple with the given parameter. So it does this. It calls m handlers 0 with the violated parameter, m handlers 1, the violated parameter, and so forth. So again, it is quite a simple implementation. There's a bit of template in those internal functions, but it is definitely doable. Yeah. Now note, I have not included, again, any of this specific PubSub framework specific code here. Like here, we just made the operator paren. In order to tie it into a PubSub framework, you need some logic that subscribes to the signals that you want to monitor, and it should call the operator paren when they change. That's basically what it boils down to. So it's not a huge task actually to do this. One thing that we would like, though, which I haven't covered yet, is that these conditions until now, they have just been hard coded. We say it should be larger than 1 and smaller than 10, for example, but that's not really flexible. We would like these conditions to depend on another signal, which can be some kind of parameter, which you can set at runtime as well, and the monitor should be run again, ideally. Now for this, we could make a specialization of larger than, which takes a reference to some kind of parameter type, which could be the minimum, and then it just checks the value for this reference. The problem with this is there's a bit of problems actually. So the class that owns the monitor, like the class that has instantiated this monitor, it needs to have an instance of this parameter. I would like to avoid that if we could, because it doesn't really belong there. It should belong in the monitor. And also, I think that's a bit more tricky, is that if this parameter changes during execution, then the owner needs to, like the one that created this monitor class, it needs to make the monitor check whether these conditions are violated. So it needs to subscribe to this parameter and then call this operator paren whenever it is changed. Because that's not something that's done by the monitor. And the problem here is that this larger than method doesn't know that it belongs to a monitor. It is just returning a callable. So it has no clue that it's actually part of monitor. You could actually use it for any kind of other thing where you want to check if something is larger than something else. So how do we couple this larger than specialization, or this larger than condition to the monitor to be able to access this PubSub framework? And we could give the larger than this O parameter as well. That would help a bit. Then we could get updated the parameter, but we would still not be able to trigger the monitor, which is ideally what we would like. Now, one solution to this is that we could make all of the conditions we make take an implicit first parameter, which is a handle to the PubSub framework. So a bit like this O parameter here. So instead of having a larger than function that just returns a callable which takes a single value, it also needs to take some implicit extra parameter, which is a handle to this PubSub framework. And if you don't want to subscribe to anything, if this is not a parameter that can be subscribed to, then you just don't use this first parameter. You just throw it away. But if you want to subscribe to something like this, my lower bound param type is a type I can subscribe to. In that case, we do use this implicit first parameter. And we have in our Lambda, we have a subscribed Boolean as well that checks whether it has subscribed. So when the monitor does its first check, which it usually should do at construction time, because we always want this monitor to run, then we will also subscribe to this parameter, and the PubSub here should also trigger the monitor again once this minimum parameter changes. So that is a way to get this kind of functionality, which we would like, where we can have parameters that are part of this PubSub framework as well, so that they can trigger the monitor whenever parameters change as well. Now it's not only the signals that will trigger a check, it's also the parameters. Now, granted, I'm not entirely happy with this solution because it's very invasive into all of these conditions. All our conditions now suddenly needs to take this implicit first parameter. So I would like to have a better way of doing it. I haven't yet come up with a good solution. I thought about maybe you can do some SVNA template trickery to try to call without the implicit parameter and otherwise call with the implicit parameter, and it will all just go in. But I'm not sure I'm not sure that's a good way to do. That's still work in progress. So one last thing here. Should we override and for the handlers? Here we look a bit at readability again. Should we do something like this so that we can say the handler should make an immediate alarm activation and a delayed alarm deactivation of an alarm? It reads out very well. The problem is that it doesn't really make sense logically. I think here it falls under the category never do this. Just because it reads out fine in text doesn't mean that it makes sense logically. I think that this is a case of just because we could do this doesn't mean that we should. And handlers are not really logical types anyway. The conditions, I would argue, are a kind of logical type. Handlers are not. They don't return anything. So yes, that's it. And I'll answer any questions that you might have. I have a GitHub repository here where I'm playing a bit around with this. It's, as I said, it's not something you can take out and use just as it is. It's a bit of a playground for me to play with this, but you can have a look at it if you find it interesting and want to clone it. You can do that. Thank you.
Thank you for your talk. That was really a good overview on and how design interfaces with this. So if you have questions and want to do a further discussion on this with Nikolaj, join him in the launch table, and then he'll be there. And I hope that he could answer all your questions in chat. And so join him in the launch for the questions if you have any questions left, or want to give him feedback and ask him about his GitHub repository, for example. And with that, we're going to go now in a break, and then the next talk will continue. And in the break, you might want to join Nikolaj at his table. Thank you, Nikolaj. It was a great talk.
Thank you.